Alright, hi everyone. So we're back after just going through electrons, protons, and neutrons. And so I have a little warm-up that's here. Take a second, I'd like for you to jot down the table and just try to fill in the table as you see it. When you're ready, come on back and we'll go over the answers just as a continuation from your last activity. So pause the video, give it a try, and come back when you're ready. Alright, so hopefully you've had a chance to give the warm-up a try, and if we run through the different values, I'll give you a second to kind of take a look and check off your answers, see if you're on the right track. So again, just pause the video, check your answers, and we'll move on. Alright, so we're going to run into a little bit of history in this section on atomic theory, so I would encourage that you go about this as best you can in terms of taking in some of the information. I'm not necessarily looking for exact dates per se. You should have them in some sort of order in terms of who did what, but not like specifically in 1862 did this happen, but more in lines of maybe in the 1860s or in the 19th century, just to have a kind of a chronological order of events happening. So when we talk about atomic theory, we're going to develop these models of matter. So scientists have observed and questioned and theorized for centuries about matter. So in an attempt to explain the evidence around them, many models of matter were developed. They've been modified, they've been combined, rejected as new evidence came along, which is kind of the whole way that science works. Basically, as new evidence comes along, it gets challenged, and if it passes those challenges, then it kind of becomes the current train of thought until something new comes along that either edits it or changes it completely, or strengthens the already made claim based on the evidence that's found. So as you're jotting things down here, or reading through the information, taking it however best you feel like you can learn, I don't think you need to copy every single thing down here, but again, you're more focusing on the people, the types of model that they came up with, and roughly in some sort of order as to when that happened from the oldest to the newest. So our first one, about 450 BC, we get this 4-element model. And then it was a Greek scholar, Empedocles, believed that all matter was composed of 4 fundamental substances. So we had earth, air, fire, and water. And between those 4 substances, you could take things in parts and mix them together. So like, for instance, the desk you're sitting in could theoretically be made up of a combination of 4 parts water, 5 parts earth, 2 parts fire, to combine together to make objects, and that's how things were composed at a fundamental level. And this view was actually accepted for almost 2,000 years before really any meaningful evidence could be gathered that could change people's minds and how this stuff worked, how matter was composed. So he wasn't the only model that was around then, though. So about 400 BC, so 50 years difference, Democritus suggested that all matter was made up of these tiny particles that couldn't be broken down any further. And he called these particles atomos, which is Greek for indivisible. We can see kind of how this model actually is very close to our current understanding of what we see atomic models and subatomic particles to be. So different elements, they're composed of different atoms, which were believed to be different sizes and have, different geometric shapes, and they were always in constant motion. So this idea, although more in line or more accurate with our current view, wasn't as widely gained because it was, the idea of something so small that you can't see it with the naked eye. How could that exist, right? How could that be a thing? So just a couple of little parts. Empedocles, he's got his 4-element model, so you can see if you combine like air and water, things would be wet, or water and earth, that might be cold, right? You'd have different characteristics that you could make up parts of these things. Whereas Democritus in his model, everything was based on shapes and different geometric properties. And so they're always in movement, they're always moving around and doing what they're doing, but they're all kind of unique in their own right. And so this idea that they're indivisible, they can't be broken down any further, there's a lot of characteristics here that we can use moving forward with our own knowledge. So moving on, AD 500 to 1600. So again, remember, for almost 2,000 years, this stuff was kind of relatively known as under a certain viewpoint. So we move on to alchemists. They're a combination of a philosopher, a magician, and a chemist. They believe that metals can grow like plants into gold. So if you mix the right things together, you could actually take something that was invaluable and mix it in the right proportions and turn them into something valuable, such as gold. And alchemists tried for centuries to turn cheap metals like iron and lead into gold by performing these various experiments. And so you may end up maybe have heard of alchemy before, alchemists in terms of potions and mixing things together, and oftentimes that's what they're trying to do. So they're trying to mix a few different things together to come up with something that is a little bit more valuable that then they can turn around and sell. And so oftentimes if they were successful in terms of making something look, say like gold for instance, people could perform little tests on them, whether they scratch the surface of them, or because gold is fairly soft, or even bit into it, you could often leave dents. And iron and lead are not necessarily soft metals, and so you could tell differences in that sense from, say, fool's gold or from other fake imitations of it. So they devised these chemical symbols, though, for elements and compounds, and they also invented laboratory tools that we still actually use today. So some alchemists that were able to kind of come along with different ideas in terms of what they did in their experiments actually were meaningful experiments. And so we could take some of those ideas and still use them in today's stuff, things like beakers and filters and stirring rods. The things that they use to perform their experiments, we can use to our advantage as well. So in 1650, we have our next person, Robert Boyle. So he devised a new definition for the word element. He said it was a pure substance that cannot be chemically broken down into simpler substances. So an element is our basic building block. He also didn't believe that air was an element, but rather it was a mixture, and which is accurate. And then 150 years after that, late 1700s, Joseph Priestley may have isolated oxygen, but he actually didn't realize at the time that it was an element. And Henry Cavendish, another one, discovered that flammable gas hydrogen, and he found that out by mixing metal with an acid. So he actually was able to find hydrogen gas through mixing metals and mixing metals with an acidic substance, and the gas that was given off being flammable and being hydrogen gas. So he discovered that hydrogen would react with oxygen in the presence of enough energy, and water was produced. And when we talk about energy here, really we're referring to heat. Up until then, scientists had believed that water was an element as well. So some different pictures just from kind of reimaginings of older times, that kind of stuff, just in terms of what they might do. Some of the different devices that they would have used to mix things together, and as well as things to create a little bit of air to feed a little bit of flame, or mixing different chemicals together to maybe try to come up with something different. And then our different people, so our Robert Boyle, Joseph Priestley, and Henry Cavendish. So, 1800s, early 1800s. So by this time, it was generally accepted that matter was made up of elements. John Dalton, he published a theory called the atomic model of why elements differ from each other and from other non-elements. So all matter is made up of atoms, which are particles that are too small to see, and each element has its own kind of atom with its own kind of particular mass. And compounds, they're created when atoms of different elements, they link together to form molecules. And so you can start to see how this current structure, even though we're early 1800s, is very familiar to how we kind of understand how elements and how compounds are formed. Things are getting a little bit more specific, even in terms of the naming, and the words that they're using are similar words that we would use today. So also kind of thought that atoms cannot be created, destroyed, or subdivided in chemical changes. And in Dalton's atomic model, an atom is this solid sphere. So there's really nothing outside of Dalton's model. He's got no concept of electrons or protons or neutrons, so he can't, visibly notice these electrons that are buzzing around outside of the atoms that are there. He just thinks that they're a solid sphere. And he actually coins this as the billiard ball theory or pool ball theory in that process. So in the 1800s, we have this modified atomic model. So as from 1808 moving forward, matter was observed to produce positive and negative charges. So all of a sudden now it has charge. A model was created that suggested that these negatively charged particles could be separated from their atoms, and they could actually move on to other atoms as well. And so these negatively charged particles, they're obviously ones that caught a lot of people's interest because of their ability to actually change how atoms form and how compounds form. Michael Faraday, he found that an electric current could cause chemical changes in some compounds and solutions. So by gaining electric charges, that's where we start to come up with this idea of ions. So some atoms can actually start to take in extra electrons, or maybe they donate extra electrons to another atom, and when that happens, we get this term ions, and that's going to be really important in later talks. So in this modified version of Dalton's model, matter must contain positive and negative charges, and opposite charges attract, like charges can repel. And so atoms combine to form molecules because of electrical attractions that happen between atoms. So all of a sudden we get this idea of force and electrical attraction when things have charged particles to them. So when we have, say, more electrons than we need, or maybe not enough electrons, you can get this idea of compounds that might form between atoms and start to form multiple atoms combining together. So just a couple little pictures. So John Dalton and his concept of this billiard ball theory. So they're almost like visualizing it like pool balls. There's nothing on the outside. They're smooth. And Faraday takes Dalton's idea and basically adds to it by understanding that there's this charge between them that can attract these things together. And so the idea that they're not just, empty structures, but they actually are doing something. They contain charges. So after that, we move to 1904 and move on to the next model, which is the Raisin Bun Model. J.J. Thomson, he discovered that these negatively charged particles were far lighter than the heavier positive particles. And from that, he got the idea of this Raisin Bun Model. So atoms contain very light, negatively charged particles called electrons. And so he's the one that's really coming up with this idea of the electron. The rest of the atom is a sphere of positive charge, and the electrons are embedded in that sphere, making the atom uncharged overall. And so his concept was this idea of a Raisin Bun model, where you'd have an atom, but you'd have these electrons that would kind of be stuck to them overall and on the outside. So after that, Nagaoka, he modeled the atom as this large positive sphere, and instead of the electrons being stuck to the sphere, he thought it'd be more like a ring going around it. So he kind of came up with this idea and likened it to the planet Saturn. And so basically just saying that we had this planet and we have electrons that are buzzing around. And so really our model is starting to become a little bit more sophisticated as we understand more and more about electrons and how they behave inside of these atoms. So from a semi-local perspective, from a Canadian perspective, 1911 we have the nuclear model. So we had the billiard ball model from Dalton. Then we moved into the idea of Faraday adding charge. Then we started to talk a little bit more about J.J. Thomson and his discoveries with the Raisin Bun model, which led to Nagaoka maybe talking about more like a planet Saturn, like a planetary idea. And 1911, the nuclear model. So Ernest Rutherford, he's in McGill University in Montreal. He came up with a new model to explain his experiment that basically was designed to test both of these previous models. He fired these alpha particles through a thin sheet of gold foil, and what he was expecting was that really there's nothing there and it should just pass straight through. And what he noticed was that some of them were reflected off at odd angles, and even some of them bounced straight backward. And the only way that could happen is if there was something there that they couldn't see that was causing it to hit and bounce back like a hard object. So he explained his results by creating a new model called the nuclear model, and saying that an atom has a tiny, dense positive core called the nucleus that contains positive particles. The nucleus is surrounded mostly by empty space, which is the reason why the majority of them, of those those alpha particles, was able to fire through that gold foil, but was actually causing some of them to bounce back in different areas. So we had our two, and then we have this idea, 1913, of this planetary model. So there's this whole concept of different colors of light having different energies, with blue being the strongest light that's there. And when an element or elements are heated in a flame, they show a few specific colors. So these definite energies of light couldn't really be explained originally in what we thought. Niels Bohr came up with a planetary model, which basically took Rutherford's model and added on the idea that they had orbits that they followed around. So these electrons actually would have a predictable path that they might follow around a given atom. And if we understood that they weren't just kind of everywhere and scattered around this nuclear model, then the Bohr-Rutherford model kind of combines both things together. So electrons move around the nucleus, and they have this definite amount of energy. The farther away an electron is from its nucleus, the more energy it has, as well as coming up with this first concept of what it takes to fill an orbit or a shell or a ring, if we can imagine that. So the order of filling the electrons in the first 4 orbits is 2, 8, 8, and then 8 moving outward. And we'll talk and spend a lot of time kind of going through those, so don't worry if you don't understand all that stuff right away. Just more of the idea of Bohr coming in and redefining or adding to Rutherford's model and making it so it's not so much a nuclear model that is everywhere, but these electrons are specific and are kind of connected in predicted pathways around the nucleus. So electrons are more stable when they're at lower energy and they're closer to the nucleus. This model explains how electrons can jump to higher orbitals. When we say jump really exists when we start to talk about heat being given off. So if we were to burn something, we might cause color change, for instance, to happen. Well, that happens because these electrons are moving around from one to the next. We say that they're in an excited state when that happens, when it moves up. These unstable excited electrons, they fall back into their normal, more stable, low energy orbitals, which is their ground state if we were to take away that energy. So if this were to see kind of how this stuff burns in flame, for instance, an almost colorless ethanol flame without any chemical things added in, so it just has a blue shape. And then if we start to add different things, you might see lithium chloride here, a strontium chloride, calcium chloride, and how when it's introduced to an ethanol flame, it gives off different colors. And if we understand or visualize how this happens here, let's say that we have one of our electrons, say the one in the lower shell, and then we were to add a little bit of energy into it. Basically what would happen is we could excite that electron to bounce up to another shell, and this energy transfer from one shell to the next, that's what causes the light that we see, or the heat that's given off. And then as it's cooled down, basically this thing would end up going backward. If we can get it to flip in the right direction, it would basically go backward to the other direction and would fall back to its original place. So there's a lot of history there. There's a lot of things to go through. You would have answered some questions on these already as well, so you're using these as kind of just like a guideline to go through. But basically, you're following the history of the model of the atom, starting from Empedocles and Democritus kind of going through the different people, the different things that they discovered, and what they did, not necessarily specific dates, and not remembering every little detail along the way, but really just kind of taking in a general overview of the history of the model of the atom. So from here, we'll take a look at the Bohr-Rutherford model in the next video.